This talk deals with the components of the EEG machine and with electrical safety. This is a photograph of Dr. Berger's EEG laboratory. The picture was taken between 1926 and 1931. This is a recording he made in 1936. As you all know, Dr. Berger is considered the father of modern EEG. This is a photograph of an EEG laboratory similar to those that were around when I trained. The EEG machine at the time recorded brain activity in an analog fashion, and they were very simple. This is a blueprint of such a machine. It was connected to an electrical outlet by a plug. It had a cord, a transformer, an on and off switch, electrodes, an input board, an input selector switches, amplifiers, which include differential amplifiers and single-ended amplifiers, low frequency filters, which consist of a capacitor and a resistor, high frequency filter, which consists of a resistor and a capacitor. I have a mnemotechnic rule to remember the order of capacitors and resistors in low and high frequency filter. The mnemotechnic rule is to remember the name Carlos Rich. C stands for capacitor, R for resistor, and L for low. This reminds me that the capacitor goes before the resistor in a low frequency filter. In the next word, the R goes before the C, and it is followed by an H. This reminds me that the resistor goes before the capacitor in high frequency filters. Next, we have the 60 Hz filter, which is made of an inductor and a capacitor. And the last element of the machine was the writing unit. Such an equipment could easily be separated into two strands. The electrical strand that goes from the plug to the writing unit and back to the plug, and the brain strand that goes from the electrode or electrodes to the plug going through the writing unit. So those are the components of an all analog EEG machine. This is a newer EEG machine. They are certainly more complicated. They have a base unit called the EEG machine proper, which includes a video camera and a screen, and two separate components. One that is called the brain box that houses the input selector switches along with many other elements, and the input box. The product of the modern EEG machine is a digital record. In this frame, I have constructed the blueprint representing a modern EEG machine. As you can see in this frame, I have removed some components to show you the electrical strand of the machine. And in this new frame, I have introduced the components that I had just removed. They represent the brain strand of the machine. I will start describing the new EEG machine by telling you about the components of the brain strand. The brain strand starts with the electrodes, that is with many electrodes, but here they will be represented as one, as will be the amplifiers. The electrode is a very important component of the EEG machine. It has four attributes. Electrodes act as transducers. The transducer function is the most important function of the electrode, and I will spend a few minutes talking about it after I finish listing all the other three functions of the electrode. One of the other three functions is the behavior of the electrode as a battery is a source of electrode artifact. Electrodes also behave like low frequency filter. Low frequency filter has little influence in the function of the electrode, and they also behave as frequent dependent filters. To understand the implication of the frequent dependent filter of the electrodes, we have to understand the concept and math that governs Warburg impedance. I will not spend any time explaining it here. If you're interested, please watch the video on electrodes in this channel and you will get a basic understanding of it, I hope. Now that I have listed all the functions of the electrodes, I'd like to spend a few minutes talking about its transducer function. The first step to understand the transducer function of an electrode is to consider the electrode as one component of a unit that includes the electrode, the skin, the gel, the electrical double layer, that is the area where the gel abuts the electrode itself, which has three components: the disc, the wire, and the receptacle. The receptacles we use at the moment are called female connectors. The purpose of this unit is to carry the electrical activity generated at the brain all the way to the receptacle. The current is first carried by ions and then by electrons in the electrode. So the current generated by the brain are moved by ions and then by electrons towards the EEG machine. This transfer of charges from ions to electrons take place because the electrical double layer has a transducer function. But it is important to realize that just as important as the charges moving from the brain to the electrode, it is for the charges to move from the electrode to the brain. So again, this is accomplished because of the transducer function of the electrical double layer. All these add up to the double layer being a two-way transducer that allows the transfer of charges from the gel to the disc and from the disc to the gel. This ability to transfer current from one medium to another is, as we have already mentioned, the most important function of the electrodes. This ability, that is the ability to carry charges back and forward, is called reversibility, and it is the hallmark of a good electrode. And the best and most used electrode, among other things, because of its good reversibility, is silver chloride electrodes. Now, after having talked about electrodes, I like to talk to you about the input box. This is an old and not very clean input box, but I like the picture. In this frame, I have marked the spot for the reference electrode. In our lab, we put the reference electrode in the midline frontal region. This is the spot for the ground electrode. We put it in the midline behind the reference electrode. The rest of the scalp electrodes, here indicated by the arrow, are placed according to the 10-20 system. So as you can see, we put the reference electrode in front of FC and the ground electrode just behind FC. It is of paramount importance to realize that digital EEG equipment, that is the digital EEG, gathers electrical information from the brain by using a single reference entering through each amplifier, as it is shown in this frame. Notice in this diagram that not only is the ground electrode the one that is connected to all the differential amplifiers, but it is also the reference electrode that connects with all the differential amplifiers. This provides a fixed value to each electrode, which can later be used to develop a bipolar recording or a referential montage, let's say to the right ear or the left ear. Before leaving the input box, I'd like to make another comment about it. Remember that the impedance of an electrode, here represented by the ZX, has to be smaller than the impedance of the input box. So the input box impedance, in order to record a good EEG, has to be much higher than the impedance of the electrode. It is said that it has to be at least 100 times bigger than the impedance of the electrode in order to diminish the possibility of artifacts contaminating the EEG. The input impedance is sometimes referred to as the amplifier impedance. After these comments about the input box, I like to consider the component that is immediately attached to it. This component is housed in the segment of the EEG machine referred to as the isolated amplifier component. And the component, as you can figure out, is called a differential amplifier. The symbol for the differential amplifier is a triangle with three prongs, as we have already seen. As you recall, one prong goes for the probing electrode in the input box, the other is attached to the ground, and the other one goes to the reference. I have simplified this diagram by adding letters to represent the connection of the prongs in the amplifier. I have done this to illustrate the function of a differential amplifier, and for this purpose I have added two waves. The wave entering through electrode connected to FP1 I have placed now inside the amplifier without any modification. The wave entering through the reference I have inverted. I have done so to highlight the function of the differential amplifiers. The function is to subtract what comes through the reference from what comes through the probing electrode in order to capture the difference between the two. The result is, as you can see in this frame, a smaller wave than one entering the amplifier through the probing electrode, in this case through FP1. Now I am going to introduce another example. Here I am presenting the FP1 and the reference prongs with two equal waves. The differential amplifier will do its function. The wave coming through FP1, that is through input 1, will not be changed, but the one coming through input 2 will be inverted. This will result in a flat line coming out of the amplifier. This function is called common rejection because it rejects what is common between the two waves. The common rejection mode of a modern EEG machine is at least 1 in 100,000, and in most instances it is about 1 in a million. The ground in the differential amplifier, so the wave coming through input 1 is compared with the ground, and the wave coming through input 2 is compared also with the ground, thus providing stabilization of the amplifier. After the differential amplifier, I like to talk to you about this element I am pointing in this frame. This element is called a floating ground. The floating ground is not a piece of ground in the sky as represented in this frame. The floating ground is a piece of equipment that only costs about $350 if you buy it secondhand, but it is vital for the proper functioning of the differential amplifiers. It is nevertheless represented in the same fashion as the usual ground. The only difference is that it is surrounded by a circle to indicate that it is isolated and not connected to Earth. After the floating ground, I like to consider the structure being pointed out. This structure is a light-emitting diode. A good way to understand light-emitting diodes is to depict them as a bulb being energized by a battery, as you can see in this frame. So we have a battery, a light bulb, and a voltmeter represented in this frame. Inside the light bulb, we have a light emitting device and also a light receptor cell. The light emitting device produces photons that are captured by the light receptor cell. So electrons from the light emitting device become photons, which then at the light receptor cell become electrons. These electrons then are captured in the wire going towards the voltmeter, and they make the needle move, reflecting and increasing voltage. The symbol for a diode is a triangle with a rectangle at the apex of the triangle, and the symbol for a light emitting diode is constructed by adding two arrows to the structure as you see in this frame. So as you can see, we have used a battery to explain the function of a diode, but a similar explanation can be made substituting the battery for the brain. You can see why the brain could gain safety by the use of a light emitting diode, since current can only travel in the direction away from the brain in this device. So first, current travel from electrons to photons, and then from photons to electrons. So light emitting diodes allowed current to go in one direction only, the direction of the EEG machine and the computer, and in conjunction with the floating ground renders the section of the EEG pointed by the arrow isolated from the rest of the EEG. So the name isolated amplifier section is used for this region. And that is also why the next section is called the non-isolated section, since it is connected to earth ground, as you can see. The non-isolated section of the EEG machine also contains amplifiers. They are called single-ended amplifiers. Single-ended amplifiers only have two prongs. At input 1, I have introduced FP1 as the source of brain activity, and at input 2, the ground. Notice that the ground is not surrounded by a circle as we did when we showed a ground in the isolated section of the EEG. This is so because the ground related to the single-ended amplifier is connected to earth ground. So let's say that a wave entering input 1 from the left frontal or prefrontal region is 5 microvolts, and it is compared with the activity arriving from the earth ground that should be 0 or close to it. The consequence is that the single-ended amplifier will amplify the signal. In many instances, it can amplify it up to 1 million times. Next to the single-ended amplifier, we have the anti-aliasing filter. Anti-aliasing filters have the resistor before the capacitor. That is, electricity first travels through the resistor and then travels through the capacitor. Therefore, they are high-frequency filters. The purpose of the anti-aliasing high-frequency filter is twofold. First, to prevent high-frequency, not clinically significant wave from cluttering the capacity of the computer of the EEG machine to handle mathematical operations, and secondly, not to distort waves of clinical interest, which in the regular EEG are waves with longer than 20 millisecond duration in the high-frequency range. The usual way of thinking about high-frequency filters is as strainers that, when confronted with waves of different frequencies, will let those with high frequency go through to the ground and therefore disregard them, while keeping those with slower frequencies inside the circuit for further processing. This way of thinking may in reality be a hinder to understand filters in general and anti-aliasing filters in particular. A more sound way, but a slightly more difficult way to think of anti-aliasing filter, as it is for all filter in clinical neurophysiology, requires that we understand the concepts of cutoff, which is the parameter that is used to name a filter, and roll-off, that determines the steepness of the cut produced by the filter. To understand these terms, it is good to start with a chart representing frequencies in hertz in the x-axis, as I have done in this frame, to which I have added their corresponding duration in milliseconds and seconds, and to place amplitude, which I have added in the x-axis as a form of percentage. This percentage of amplitude corresponds to the percentage of a wave allowed to go to the computer for further manipulation. So, in case of the anti-aliasing frequency filter, which consists of a 100 Hz high-frequency filter, implying that a 10 millisecond wave will be reduced to 70% of its prior anti-aliasing filter amplitude by such a filter. And in addition, and just as important, for an anti-aliasing filter to meet its goal of not allowing wave of no clinical interest to go to clock the computer while allowing clear passage to wave with clinical interest, is the roll-off specification of the filter. The roll-off specification of a filter is given in dB per octave. Most currently used anti-aliasing filters have a roll-off of 12 dB per octave. In this frame, I am representing the placement and the steepness of an imaginary 100 Hz high-frequency filter with a 12 dB per octave roll-off by a dashed red line, as you can see. Now, in addition to the dot I used to represent 70% as it is shown in this frame, I will use another dot to represent a wave of 220 Hz. As you can see, this wave is outside the red dashed line, implying that it will be not taken into account by an anti-aliasing filter of 100 Hz with 12 dB octave. So the amount of this wave that will go through towards the computer will be 0. This fulfills one or the first goal of an anti-aliasing filter, which is not to clock the computer with frequencies that are considered of no clinical significance for EEG interpretation. On the other hand, a 15 Hz wave, that is a wave of 20 milliseconds, will be allowed to go through the anti-aliasing filter with no alteration. This fulfills the second goal of an anti-aliasing filter, that is to allow clinically significant waves to go unaltered to the computer for further manipulation. So that is for anti-aliasing filters. And now we will go to tackle the computer. The computer has three primary functions. The first function is converting analog signal into digital signal. The second is further filtering of the EEG activity. And the third is representing this activity in the form of waves in a display monitor. The first computer function, as we just mentioned, is one done by the analog digital converter. Digital converters have horizontal resolution and vertical resolution. Let's first look at horizontal resolution. So horizontal resolution can be explained by looking at this analog wave lasting 1 second and relating it to a digital converter. Every digital converter has a fixed sampling rate. The more the sampling rate, the better the converter and the more expensive the analog to digital converter is. So let's say we're cheap and we buy an analog to digital converter that takes 10 samples per second. Such analog to digital converter will produce a signal with 10 dots per second, with each sample occurring at a time interval of about 100 milliseconds from each other. The appropriate horizontal sampling rate was considered by two scientists, one named Claude Shannon and the other one Harry Nyquist. They formulated a principle that is now called the Nyquist principle, that states that in order to reproduce an analog wave digitally, at least 2 points per wave are needed. Yet, the rate of 2 sampling per wave is insufficient to accurately reproduce a wave for EEG interpretation. So, the current recommendation is to use a sampling rate of at least 6 times the frequency of the anti-aliasing filter. Therefore, currently, the recommendation for analog to digital converter is that it can sample 600 times per second. It is important to stress that when we talk about horizontal resolution, we only have to consider one parameter, time and how many samples over time. Now I'd like to address vertical resolution. Vertical resolution can be approached in a similar fashion as we just did for horizontal resolution, but it is a little more complicated. First, we have to remember that time resolution can be applied to all channels, whereas horizontal resolution refers to individual channels. And secondly, that whereas when considering horizontal resolution, we only have to consider sampling rate per second, when considering vertical resolution, in addition to having to consider sampling rate per microvolts, we also have to consider the amplitude window that we're going to use. So, as we have just stated, vertical resolution involves 2 parameters. First, the first one is the sampling rate, which is given in sample per microvolt per channel, and the second, which is the range of the amplitude window we're going to use. I will first address the sampling rate. Let's just say that the sampling rate of an analog digital converter we are using takes 4 samples per microvolt per channel. And now I will proceed to address the amplitude window. The amplitude window, which determines the maximal amplitude of a wave that will be allowed to go through the anti-aliasing filter without being clipped, is selected by the machine manufacturer. The usual amplitude window in most EEG machine is 1000 microvolts. I will explain the importance of having the right amplitude window in the next few frames. In this frame, I am representing between the yellow lines an amplitude window of 1000 microvolts. Now I am introducing a wave of 750 microvolts. As you can see, the wave is not clipped at the top or at the bottom. But let's say that we're using a window of 500 microvolts to analyze the same wave. As you can see, the wave does not fit the window, so it will be clipped, and thus the configuration of the wave will be different. The wave will be even more distorted if we use an amplitude of 250 microvolts, as I will show you in the next few frames. Here I have introduced the same wave, but as you can see, it is significantly clipped. So now that we have shown the effect of the amplitude window on a wave, I will go back to the original frame in order to continue talking about other factors that influence the digital signaling. So if we go back to the 1000 microvolt window, which is the one used by most EEG manufacturers, thus, given that the analog data converter we got takes 4 samples for each microvolt, then the number of samples the converter will take to register 1000 microvolts is 4000 levels. So we can say that the converter has 4000 potential levels for that channel. The term used to refer to levels in the computer lingo is bins. In addition, since computers work with a binary numerical system, further adjustments are needed regarding the amplitude resolution. First among this arrangement is to use a binary friendly number to indicate the number of levels. So instead of using 4000, the number used would be 4096, which corresponds to 2 to the 12th power, which again in computer lingo is called 12 bits. It is the number of bits that is used to label the analog to digital converter. So in this case, we would talk about a 12-bit analog to digital converter. So if we have a 12-bit analog to digital converter and we use an amplitude window of 1000 microvolt per channel, the interval between each bins will be about a quarter of a microvolt, which will correspond to about 4 bins per microvolt. If you have any doubt, take a few seconds to execute the operation in this frame and you will see how it works. Now notice that if we double the size of the amplitude window, that is, if we make the window 2000 microvolts, we would also double the size of the interval between the bins, thus decreasing the number of bins to 2 per microvolt. Were we to go back to the 1000 microvolt window, and instead of increasing the window, we would decrease the amplitude of the window to 500 microvolts, we would have decreased the interval between the bins to 1/8 of a microvolt, thus increasing the number of bins per microvolt to 8. I will at this point give you an example. Using a 12-bit converter with 1000 microvolt window with a horizontal sampling rate of 600 samples per second, as I have represented in this frame, and let's say that we want to look at 20 milliseconds of a recording using these parameters. So in 20 milliseconds, using an analog to digital converter with the just mentioned specification, we would have 12 samples or dots. In this frame, you have the problem set up, and here I have executed so you can see where the 12 comes from. So we have 12 sampling points, which I have now expressed as binary numbers. And let's say that we want to represent a 3.75 microvolt segment of a wave, which are represented in 16 bins with an interval of about 1/4 microvolt as represented in this frame. This corresponds to about 4 bins per microvolt, as you can see. Now let's express the microvolts in binary numbers. In this new frame, I am extending the levels corresponding to the microvolts to include the 20 milliseconds. And now I have added the segment of the analog wave that we want to digitalize. In this frame, I will illustrate the digitalizing process. So let's start at 0, 0, 0, 0 in the x-axis. At this point, the analog to digital converter will choose 1, 0, 1, 0 in the x-axis. Notice that the converter has placed the dot at 1010 bin and not at the 1011 bin. This is because this level has not been reached by the wave, and the analog data converter only jumps from a bin when it has reached the next level above it or below it. So once the value for horizontal 0000 has been placed, thus the analog converter moves to the next horizontal position, in this case to the horizontal 0001 position. The location of the bin for the horizontal 0001 is accomplished in the same fashion and following the same rules, and the converter will mark the placement. The same is done at horizontal level 0010, placing the mark below the analog signal. In this frame, I have enlarged the area so we can better appreciate the relation between the analog signal and the dot. So the process will go on for every horizontal number until all locations are chosen and marked. In this frame, I have introduced all the dots found in the grid in order by the side of the grid. Next to them, I have added their corresponding horizontal binary value, followed by the corresponding vertical binary value. In the following frames, I will indicate this to you graphically by drawing an arrow from the dots in the grid to the corresponding dot in the vertical column, as you can see here and here. The final point I would like to make before leaving this graph is that aliasing, that is the distortion of an analog signal as it is converted to a digital signal, always occurs when analog signals are digitalized. In order to depict this reality a little bit better, I have thickened the analog signal to better demonstrate aliasing. In this frame, I have used blue rectangles to indicate the best possible appearance of this wave segment that an analog data converter can match. This will only occur if the sensitivity of the computer screen is capable of generating these fine points. As you can see, even if that be the case, it is not perfect. Now I like to go back and show you a frame I have shown you before. As you can see, it shows parameters related to 12-bit analog to digital converters. I am introducing a 16-bit analog to digital converter. A 16-bit analog to digital converter has 65,536 vertical levels or bins. Hence, when used in conjunction with an amplitude window of 2000 microvolt, it has an interval between bins of 0.03 microvolts and accommodates 33 bins per microvolt. Were we to use an amplitude window of 1000, then the interval between bins will be 0.015 microvolts and it will accommodate 67 bins per microvolt. And were we to use an amplitude window of 500, then the interval between bins will be 0.007 microvolts and each microvolt will accommodate 143 bins. So the current standing recommendations regarding analog to data converter that I am aware of at this point is to have a horizontal resolution of 600 samples per second, an amplitude window of 1000 microvolt per channel, and to have a vertical resolution of 16-bit, which will accommodate 67 bins per microvolt. These recommendations that is, the recommendation regarding the vertical resolution of 16-bit was changed in 2016. Before, it was 12-bit. Having finished the discussion about analog to digital converters, I will now talk about filters and math. Digital filters use one of three methods of computation: finite impulse response, infinite impulse response, and fast Fourier transformer. Of these three methods of computation, the one most often used by most EEG manufacturers is the finite impulse response. And luckily for us, the engineers have designed the mathematical filters so that they end up looking or end up with a product that resembles the configuration of the waves produced by analog filters. And in addition, they have made these controls readily available to us, as you can see in this frame. Since engineers were kind enough to use math filters to mimic analog filtering, I will use the same method to explain that I used to explain anti-aliasing filters to explain digital filtering or mathematical digital filtering. At this point, I will take a few seconds to remind you of some of the characteristics of anti-aliasing filters and then proceed to talk to you about filters that we can control. If you recall, when we spoke about anti-aliasing filters, we said that since they are 1000 Hz high frequency filters with a 12 dB per octave roll-off, they would allow 20 milliseconds wave to go through the filter unaltered, reduce a 10 millisecond wave by 70%, and not allow a wave of 4.5 milliseconds or less to go to the computer for further processing. In most situations, the high frequency filter that we can manage, also called low pass filter because it lets lower frequency activity go through while blocking higher frequency activity, is set at 70 Hz. A setting that reduces the amplitude of a wave lasting 20 milliseconds some greatly reduces the amplitude of a wave lasting 10 milliseconds and obliterates wave lasting 7 milliseconds or less. The usual setting for the low frequency filter is 1 Hz. Such filter allows wave of longer duration than 500 milliseconds to go through basically unaltered, while obliterating all wave lasting 2 seconds or longer. The third type of filter that an electroencephalographer controls is the notch filter. In the United States, they obliterate 60 Hz activity, but despite their relatively sharp roll-off, notch filter affects wave of a slightly longer and shorter duration as depicted in this frame. In this new frame, I have given a green background to the frequencies captured and the amplitude reduction produced at the fringe frequencies that is produced when the commonly used filter settings are used. In this new frame, I am showing what happens if instead of us using a 70 Hz fast frequency filter, we were to use a 5 Hz high frequency filter. As you can see, the amount of wave captured would be greatly reduced. In the next frame, I will demonstrate the consequence of such choice. Here we have an epoch display with a high frequency filter of 70 Hz. Notice the wave inside the circle. Here I am displaying the same epoch but with a high frequency filter of 5 Hz. The spike is gone. Take a few seconds to look at this frame. You can choose to stop the video at this point, and I urge you to go to a YouTube and watch all the other videos related to filter. If you do that, you will get a much better understanding of filters that you will get in this presentation. You will see how filters not only affect amplitude of a wave, but they also affect onset latency, duration, peak latency, area of a wave, and also waveforms. Having finished talking about filters and math, I'd like to tell you a few things about the computer display. The display screen should be at least 1600 pixels wide and 1200 pixels high. Flickering, usually starting at the edge of the screen, is a bad sign, and it should prompt you to buy a new screen. The screen other qualifications relate to how many millimeters of a screen per pixel should there be. That is the screen per pixel proportion. The last recommendation I heard was for pixels to be square and for the screen to have at least 4 pixels per vertical millimeter. These recommendations are from 2006. At this point, I will conclude the discussion regarding the brain strand of the EEG machine and start talking to you about the electrical strand. The electrical strand of the EEG machine was built with 3 purposes in mind. The first purpose was to supply electricity to the brain strand, the second to prevent the possibility of an electric shock, and the third to shut down in the event of an electric fault. I will first talk to you about supplying electricity to the brain strand. Sadly, as of yet, we have not figured out how to use the electrical field generated by the brain to drive all the components of the EEG machine. So we need commercial electricity. We need commercial electricity to drive the input box, the isolated amplifiers, the non-isolated amplifiers, and the computer. Yet, supplying electricity for these components places the patient at risk. So first, in the mind of the engineers was to develop an energy delivery system that prevents the possibility of electric shock. For this purpose, they use several devices strategically located to reduce voltage on ground components of the EEG in direct contact with the patient, diminish stray electricity, and prevent backflow of electricity. The first of these devices will be a transformer. The first transformer encountered in the EEG machine is called a step-down transformer. Commercially strength electricity, which could be 120 or 220 volts, comes into the transformer by the primary current circuit. And making use of magnetism and coil size, the transformer changes that electricity to 24 volt current. The second transformer is just as important. This transformer is called an isolation transformer. These transformers have a ground at the primary current entry, that is where the electricity enters the transformer, as you can see pointed by the arrow, but when the electricity comes out of the transformer, the electricity will be ungrounded. To understand the safety of on-ground electricity, please view the YouTube video in this channel titled Electrical Safety. So it is the function of this transformer coupled with the floating ground and the light emitting diode that defines the first set of amplifiers as the isolated amplifiers or the isolated amplifier section. That is because to a great extent these amplifiers are isolated from commercial current by the just mentioned 3 devices. The device I am pointing to in this frame is a regular diode. Regular diodes are represented by a triangle with a rectangle at the tip, as you can see in this frame. The function of a regular diode is to transform alternating current into direct current. This is an effective method of preventing electric shock because alternating current produces more stray current than direct current. Another important device built in the EEG machine to decrease the chances of an electrical shock is the chassis. The chassis should be built from a poor electrical conductor material to avoid a stray current from the machine leaking into the ambient. In addition to preventing electrical shock, the electrical system of an EEG machine has built-in devices to stop current from going into the machine if a fault in the electrical circuit occurs. These devices are also strategically placed in the equipment. First among them is the current stopper detector. Current stopper detectors function in relation to time. Here I have depicted 2 wires in yellow carrying current in both directions. As you can see, I have placed a bar between the wires and at the top of the wire a dome-shaped structure. If at a given time the amount of current traveling in one direction is not the same as the amount of current traveling in the opposite direction, as I am represented in this figure, the bar in the middle will lift the segment of the wire on top of it, as depicted again in this figurine, thus breaking the circuit and stopping current in either direction. Most current stoppers are designed to stop current if more than 10 microamps difference develop for longer for 1 millisecond or longer between the neutral and the hot wire. Another important electrical component is the fuse. The fuse consists of a thin wire that breaks if current more than the current specified in the fuse goes through. I think of it as a weak link of the circuit. So if something is going to break, it breaks there. So despite the safety features of the EEG machine, that is all the devices put in for the prevention of electric shock and those put in to shut down electricity in the case of a fault, it is, without the human factor, a risk. So the prevention of electric shock when doing an EEG machine starts by observation. That is, observation of the person that is doing the EEG. I like to think about this in relation to a toaster. Think of the EEG machine as if you were looking at a toaster. Therefore, if you find that the chassis has bump, you should not use it. If you find that it's wet, you should not use it. If you find that it's broken, that there's a tear in the chassis, you should not use it. Look at the cable before you start a recording. If the cable is broken or torn, do not use it. Look also at the plug. If you find that one of the prongs is loose or is falling down, do not do the EEG. Change the machine. Another important thing is that it should feel right. That is, when you plug it in, you should feel that there is no unusual noises, and very often it's good if you feel there is some unusual noise to pull it out, to check the amount of pressure that it takes to put in and to put out. The force required to withdraw the ground pin of a test plug from a receptacle should be at least 10 ounces. Anyway, if any of the things are going on, again, change the machine and do not use that machine to record the EEG you had in mind. Another important thing is not to use extension cord. Remember, one foot of an extension cord is equal to 1 microamp of a straight current. Do not use cheater. These things are called cheater. Remember, do not use them. Also, look carefully at the electric outlets. If they have 2 holes, do not use them. If there is no green dot, do not use them. Only use those with 3 holes and a green dot, and only after visually inspecting that the neutral, the hot, and the ground holes look good. Do not connect a patient to equipments going to different electrical boxes because they may be connected to 2 different grounds. All equipment going to one patient should be connected to one electric box, so all go to the same ground. The equipment should be checked every 6 months. Checkup should include ground to chassis resistance, which should be less than 0.1 ohm, chassis to ground current, which most believe it should be less than 10 microamps. You should also check outlet to ground current, which should be less than 10 microamps, and you should also check input box to live current. It should be less than 10 microamps. These tests are carried out by specialized technologists using a state-of-the-art equipment and should be conducted with the equipment in open ground position and closed ground position, reverse polarity and normal polarity. It should also be conducted in open neutral position and closed neutral position. It is also important to maintain an order of operation when doing an EEG. First, make sure that the machine is off when you take it to the patient. Once you're going to start doing it, connect it and turn the machine on. Usually that is by a switch that is present either in the computer or in the main frame of the machine. Then once the machine is on and you see all the lights bright and shiny, then you do not connect the patient with the machine off and then put the machine on. You put the machine on, and only when you see that all the lights come up the proper way, then you connect the electrodes to the patient. Run the test. After finishing the test, disconnect the patient while the machine is still on. Make sure that all the wires are off the head of the patient, and then turn the machine off. So now, since we have finished talking about how to prevent an electric shock, I like to tell you what happens when things go wrong. When things go wrong, the patient or you may get, obviously, an electric shock. For an electric shock to happen, current has to go through the body. And for current to go through the body, a voltage imbalance must exist between 2 points in the body. As depicted in this frame, a circuit must be present. Current only leaves where it is if it knows that it can come back to the same place. In this diagram, the magenta arrow indicates a region of high voltage, and in this new frame, the magenta arrow indicates a region of low voltage. Now, the magenta arrow is indicating the circuit required for current to return to its place of origin. Another important condition for an electric shock to occur is that the circuit through the body is the circuit with the least resistance for the current to go back to its origin. An electric shock is considered a macro shock. Macro shocks are felt by the individual. They occur when the magnitude of the current producing the shock is more than 300 microamps. The consequence of macro shocks quoted in different books varies a little, so I will list what is listed in 3 different books. Starting with Luther's Comprehensive Clinical Neurophysiology. Next, looking at fundaments of EEG technology that specify that the current that was used for the experiment was 60 Hertz, and also clinical neurophysiology. So I will look to those 3 books for the different parameters that produce different type of clinical manifestations. I like to stress that all units will be given in milliamps unless otherwise specified, and I will assume that the specification for the current is as that used in the United States. And a point that is not clear in any of these books is duration. What is the duration of the current that was applied in order to produce the symptoms that they are describing? Nevertheless, I will go ahead and review the information given in these 3 different textbooks. I will start with threshold for sensation, and I will use 0.3 milliamps rather than the other 2, just because it is is the number that we use to define macro shock. Pain threshold is often quoted to be felt at 1 milliamp. Minimal harmless current is often quoted to be 5 milliamps. Let go current, meaning the highest current that a person can release if it's acting on a muscle, ranges from 10 to 20 milliamps. Muscle tetanic contraction, that is what prevents humans from releasing a live wire, occurs when the magnitude of the current is 10 to 20 milliamps. Syncope have occurred with currents of 20 milliamps. Mechanical injury to the skin occurs with current of about 50 milliamps. Current of 100 milliamps can cause death, and certainly if it can produce ventricular fibrillation, it can also produce death. Paralysis has been reported to occur with 5 amps. I guess that excludes the patient who had died with lesser current. Respiratory paralysis has occurred with 15 milliamps. Sustained myocardial contraction occurs with 5 to 10 amps, and burn have been reported to occur with 5 to 10 amps. In addition to macroshock, a patient can be killed by a microshock. That is an electric shock in a vulnerable patient that person cannot feel because it is less than the threshold for sensation, which is 300 microamps. In other words, current can kill you before you know that it's hitting you. This can occur in patients with indwelling catheter, especially if the tip of the catheter is close to the heart and the current source come in direct contact with the structure that is in direct contact with the catheter. But it can also happen even if the current source is not in direct current with the catheter, but there is decreased resistance at some point, making that path the easiest for current to travel. Just remember what we mentioned before, that current will always travel through the circuit with less resistance. So if current finds a circuit with less resistance through a catheter, it will take it. Overall, the vulnerability of an individual in relation to the equipment depends on many factors. But in general, appliances have been graded into groups depending on how risky those appliances are for the different type of individual. For example, Group 1 appliances are those not in direct contact with patients, like let's say a TV that you're using with a remote control. The maximal acceptable leakage current of such a device is 500 microamps. Any appliance that is in contact with a patient, that is in contact with the surface of a patient, has a maximum acceptable leakage current of around 100 microamps. That the point is that if, like for example, an EEG machine that has to be in contact with a patient should certainly not have a leakage current above 100 microamps. Now, if that same appliance is in contact with a vulnerable patient, that is a patient that has any increased likelihood of getting an electric shock, then the appliance has to have an even lower maximal acceptable leakage current. And in those cases, the maximal leakage current is 10 microamps. Neonates, that is any equipment that is in contact with the neonate, has to have a maximal acceptable leakage current of less than 10 microamps. So a neonate is considered as vulnerable as a patient with a catheter or any other condition that makes him more vulnerable to electric shock. The reason for that is that neonates are more vulnerable to electric shock. So I like to conclude this talk with two very important. The first advice is know your machine. The second advice is avoid electric shocks. Thank you.